6.3 Exponential Functions. Malthusian catastrophe, as predicted by Malthus, states that the growth of human population is governed by the rate of crop production. In the future, if the growth rate of crops decreases, then human population growth is decreased, and there might come a day when we have an extremely limited supply of food, which can cause widespread hunger and starvation. So exponential function is a reminder of how efficiently do we utilize the available resources. So these are some examples of exponential functions. The first example is world population and growth rate. So we are growing exponentially. It started to happen in the 1940s and 50s, right? Those are called baby boomers. And that's what started the exponential growing of our population. Now, why is it that time when we started it? Is because that time is when we started to make crazy advances in science and technology. So, back in the 1800s, when most people only lived to about 40, you know, fast forward 100 years and people are living to, 60 and then 70, and now the average age is closer to 80. So because of medical advances, we're starting to live longer and longer and longer, and that really happened in the early and mid 1900s. Our second chart, I'm going to read the quote underneath. It really does explain it very well. There is a continuous cycle of innovation that is necessary in order to sustain and avoid collapse. The catch, however, to this is that you have to innovate faster and faster, so that the image is that we're not only on a treadmill that is going faster and faster, but we have to change the treadmill faster and faster. We have to accelerate on a continuous basis, and that's by Jeffrey West. So that quote in this picture is from a TED Talk. It's super interesting. If you just look up the surprising math of cities and corporations, you can find it on YouTube. It's 17 minutes long. It's actually really, really interesting to watch. So this graph is taken from that excerpt of we have to keep growing or we'll collapse. So let me explain this graph a little bit better. So you know how you have like a bunch of markers and you put them together like a lightsaber or a sword, and then you put it too high and it collapses? It's because it's going too high and it collapses, right? So this is our marker sword or lightsaber, and before we get too high, we have to rebuild and rebuild and rebuild. But every time we rebuild, we have to rebuild faster and faster and faster and faster. So if we take that to an example of science, especially with available resources like food and water, we have to continuously come up with innovations faster and faster and faster to be able to feed our population. So if we don't continue to innovate, we will start to die off and have starvation, stuff like that. And it's already starting to happen. So agricultural engineering is literally the hottest degree you can get. And to me, it's the most important degree that you could get right now, because it's how can I grow these crops better? How can I utilize less water to grow more? And that's all agricultural engineering. Alright, these are the laws of exponents, just in case you forgot. We can go ahead and just get rid of that one. Don't let it confuse you. We don't ever use that in this class. So if we're multiplying exponents, we add them. If it's on the outside, we multiply. If we have an exponent, it goes to both. A 1 to the power of anything is always 1. You're not allowed to have negative exponents. Instead, we flip it into a fraction, and anything to the power of 0 is 1. Alright, this is an exponential function, so it's like the same thing as y equals mx plus b, except this is an exponential function. So a is a positive real number. That means it has to be greater than 0. A cannot be 1, c cannot be 0, but it's a real number. The domain of f is all real numbers. The base a is called the growth factor. So that's called our growth factor. And because f of 0 equals c to the power of a, or c times a to the power of 0, c is called the initial value. Alright, we're going to identify linear or exponential functions. So to determine whether the function is linear, exponential, or neither. For those that are linear, find the linear function that models the data. For those that are exponential, find the exponential function that models the data. So we want to look at these and determine if it's linear or exponential or neither. So your x's are going to be fine, but make sure you do look at them. So my x's, it's negative 1, 0, 1, 2, 3, so it's all plus 1 for the x's. But let's check out our y's. So we want to see if, so linear is adding and subtracting constantly. Exponential is multiply or divide constantly. So let's look at our first one and see if we can multiply or divide or add and subtract. So 5 to 2, I can't divide to that. There is no number that divides evenly from 5 to 2, but I can subtract 3. So from here to here, it's minus 3. Now I need to check all the way down. So from 2 to negative 1, that's minus 3. 1 to negative 4, that's minus 3. Negative 4, negative 7, that's minus 3. So since we have a constant change of minus 3, we know that that is linear. So this is a linear function. Since it's a linear function, we need to put it into y, well, not y equals f of x, or not y equals mx plus b, but f of x equals mx plus b, because it wants a linear function. So your m is your change. So we have f of x equals negative 3x, and your b, it's always going to be listed. It's always going to be 0 number, and you're going to use that number, so 2. And that's our linear function. So since our constant change was minus, 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 that's what makes it linear. So let's see if our next one, if it's linear or exponential. So let's see if I can divide 32 to 16. So 32 to 16, I can divide by 2. Okay, let's see if I can keep going. 16 and 8, that's divide by 2. 8 and 4, that's divide by 2. 4 and 2, that's divide by 2. Okay, awesome. So we know because it's dividing by the same number that it's exponential. It is exponential, but if you think of exponents, don't we always think of multiplying? Because when we think of exponents, say like 2 to the power of 4, isn't that 2 times 2 times 2 times 2? We're going to be multiplying. So instead of using divide by 2, we use multiply by 1/2. So we always take the reciprocal, because we always multiply by the reciprocal. We actually never divide, we only multiply. So we multiply by 1/2. So now we need to put it into f of x equals c to the power of ax. In this case, we're not going to have c, so it's just f of x equals the growth factor, which is a, and that's how much we're changing every time. So 1/2 to the power of x. It's always going to be like that. It's just going to be your growth factor to the power of x. Alright, so next, let's see if we can multiply. So from 2 to 4, I can multiply by 2, but 4 to 7, that doesn't work. It doesn't work right there. So now I'm going to see if I can add and subtract. So 2 to 4, I can add 2. 4 to 2, that's plus 3. So this is neither linear or exponential because the average rate of change isn't constant at all. So this is neither. We're going to graph exponential functions. So if we don't know how to graph yet, let's do a t-chart. So I'm going to make a t-chart. And since I want the shape of the graph, I want 3 numbers. So I'm going to pick -1, 0, and 1. So let's just plug them in. We have y equals 2 to the power of 1, which is 2. Y equals 2 to the power of 0, which is 1. And then y equals 2 to the power of -1. Now we're not allowed to have negative fractions, so we flip it. So we have 1 over 2. Because we flip it and we put a 1 on top. So 2 to the power of 1 is just 2. So we get 1/2, which is 0.5. So let's go ahead and graph this. fill in our coordinate plane just using 2, because that's all we need. We have nothing higher than 2. So I'm going to plot my points, -1, and then 0.5, that's about here. 0, 1, that's about here. 1, 2, that's about here. Now, let's see if it's ever going to cross. Do you notice how it's like swooping down? I wonder if it'll ever cross. Let's see. So let's pick another negative number. Let's pick -5, because -5 is going to be way down here. So let's pick -5. So we have y equals 2 to the power of -5. So that's the same thing as 1 over 2 to the power of 5. So we have to do 2 to the power of 5. So remember, 2 to the power of 5 is 2 times 2 times 2 times 2 times 2. So 2 to the power of 5 is 32. So we have 1 over 32. So 1 over 32 as a decimal, that's really, really small. It's about 0.03. So if we were to graph that, 0.03, so our x is -5, our y is 0.03. So at -5, 0.03, we would say that's like right there. So do you think it's ever going to cross the negatives? And do you ever think we're going to get a negative y value? We're not. We are never going to get a negative y value. The reason being is because every time we have a negative exponent, we need to flip it. So it's just becoming a smaller and smaller and smaller fraction. Also, there's another reason why it's never going to cross it for this one. I'll tell you why. Do you notice that the graph of y equals 2 to the power of x won't cross into the negative y values? That is because of the horizontal asymptote, which is I call the HA. So we noticed that it's never, ever, ever going to cross. That's because this thing, this dotted line, that's our horizontal asymptote. And in this case, it's y equals 0. Why is it y equals 0? Because we have y equals 2 to the power of x. There's nothing here. There is, though. There's a 0. So that number on the outside of your exponent, that is your horizontal asymptote. That is where the graph never crosses. So the graph never crosses y equals 0. That's what an asymptote is. It's where it will ever, where it won't cross at. All right, I'm going to show you an example on my math lab on how to graph these. So I'll show you on here, and then I'll also make a video showing you to put at the end of this. So let's say this is our example. I highlighted it. So in our example, we have y equals 3 to the power of x minus 4. So what you're always going to do is your plot 0, 1 first. You always plot 0, 1 first. So you're going to hit exponential tool, you're going to click exponential tool, and then you're going to plot 0, 1. From there, you're going to shift and change the base. So the base is 3. So when you put 0, 1, this little box is going to come up, and make sure the base says 3. Then we're going to shift. So since it's minus 4 and there's nothing attached to the x, that's a vertical shift. So this is minus 4. So you're going to go left 4. And you notice it goes down 4 units. So it's never ever going to cross this one because our horizontal asymptote is y equals -4, which is that number, -4. All right, solving exponential equations. So to solve exponential equations, if a to the power of u equals a to the power of v, then u equals v. What we're looking for are same bases. The bases that you're going to use are usually 2, 3, 4, sometimes y. I mean, sometimes 5. I don't know. Sometimes y. I'm talking about, I said it. The same bases we're looking for are 2, 3, 4, and sometimes 5. Now, what does that mean? Same bases, 2, 3, 4, sometimes 5? So what I'm looking at is I want these numbers to be the same. So it's usually going to be 3, 4, 5, or so 2, 3, 4, 5. So since this is already 3, I'm going to leave it. Now I want to get 81 to have a base of 3. So I can. 3 to the power of 4 is 81. So that's what I'm going to switch it to. All I'm saying is that 3 to the power of 4 is 81. It's still the same number, I just changed the way it looks. Now since they're the same number, we get rid of those bases and we're left with the exponents. We just bring them down to normal numbers. We have x plus 1 equals 4, so x equals 3. So our solution is 3. X can be anything because the domain of every exponential function is all real numbers. So x can be anything. All right, let's move on to our second one. So I have 4 to the power of 2x minus 1 equals 8 to the power of x plus 3. So 4, yeah, that's a base I could use, but 8 can never be base of 4. Because if I try to change this to 4, 4 to the power of 2 is 16. 4 to the power of 3, I'm getting bigger and bigger. So I can't use 4. So what about 2? So I can. So 2 to the power of 2, that's the 4. Left over on top, I have 2x minus 1. And that equals, now I want to make 8 to be the base of 2. I can. 2 to the power of 3 is 8. And then still on top, we have x plus 3. Now that they have the same bases, we get rid of them and we bring everything down like normal numbers. So we have 2 times 2x minus 1 equals 3 times x plus 3. We're going to distribute. So we have 4x minus 2 equals 3x plus 9. Let's solve for x. So I'm going to subtract 3x to both sides. We're left with x minus 2 equals 9. Add 2. And we get x equals 11. So our solution is 11. And remember, x can be anything because exponential functions, the domain, is all real numbers. All right, number E, the graph of E. So you know how like we say pi is 3.14 and we just know that? Well, E is 2.71828, so 2.71. It's just a common thing in math that mathematicians said, forget it, we're going to use E, that's what it stands for, just like pi. So this is what the graph of E looks like. E is on your calculator. To get E on the TI 82, 83, 84, you press second and then divide. And that will give you E. So top left button, and then you hit divide. You see that little blue E? That's what the E is. It represents 2.71828. All right, let's solve. So we have e to the power of negative x squared equals e to the power of x to the power of 2 times 1 over e to the power of 3. Oh, I don't know what this is telling. I just says solve. Okay, so to solve exponents, you need the same base. So they kind of all already have the same base, but you're not allowed to work with fractions here. So let's just make it not a fraction. So we have e to the power of negative x squared equals e. Let's go ahead and simplify this. So that's times to the power of 2x times e to the power of negative 3. So let me take this out. 1 over e cubed is the same thing as e to the power of negative 3. Because, right, if we had the negative exponent, wouldn't we flip it and make it a fraction? So we're just going the opposite way. You're allowed to go either way. So now they have the same bases. Let's get rid of them. So we have negative x squared equals 2x minus 3. I write exactly what we have. Now, since this is a quadratic, it needs to equal 0. So I'm going to add x squared to both sides. We have 0 equals x squared plus 2x minus 3. We have to factor. So we have 0 equals plus 3, x minus 1. So we have 0 equals x plus 3, 0 equals x minus 1. So negative 3 equals x, and 1 equals x. So our solution is negative 3, 1. We like it in numerical order. Want to know why we have two answers? Because it's squared. That's why. Alright, this is where I highly suggest you pause this and try it on your own. Alright, so I hope you did. If you're like, I'm not sure where to start, okay, get the same bases. So same base. So I want you to try it now. If you didn't try it, go ahead, try it. Okay, I really hope you tried it. So we have bases 3 and 9. So 3 is already 3. I can't do anything with it. We're going to leave it 3. 3 stays 3, 2 stays 2. Everything else can be changed. So 4, anything else like that can be changed. So I have base 3, so let's make 9 base 3. So 3 squared is the same thing as 9, but we also have this 5x on top. So they have the same bases, we get rid of them and bring everything down like normal numbers. So we have x squared minus 56 equals 2 times 5x, so 10x. Since this is a quadratic, let's equal it to 0. We're going to subtract 10x to both sides. So we have x squared minus 10x minus 56 equals 0. We need to factor. So when we factor, we get x minus 14 and x plus 4 equals 0. So we have x minus 14 equals 0, x plus 4 equals 0, so x equals 14, and x equals negative 4. So our solutions are negative 4 and positive 14. So example 7, after you finish copying it, I will have with this video how to do it with your calculator. But first, I just want you to see everything. So between 9 p.m. and 10 p.m., cars arrive at In-N-Out's drive-thru at a rate of 15 cars per hour, or 0.25 cars per minute. The following formula from statistics can be used to determine the probability that the car will arrive within t minutes of 9 p.m. So the formula is f of t equals 1 minus e to the power of negative 0.25 t. Determine the probability that a car will arrive within 5 minutes of 9 p.m., that is, before 9:05 p.m. Determine the probability that a car will arrive within 30 minutes of 9 p.m. before 9:30 p.m. Graph f, and what does f approach as t increases without bound in the positive direction? So part A is asking us, when time is 5 minutes, what's the probability? So we plug it in and we get 0.713495231, which is 71%. So there is a 71% chance that a car will come through the drive-thru between 9 p.m. and 9:05. For B, we do the same thing except with 30, and we get 0.994469156, or 99%. There is a 99% chance that a car will come through the drive-thru between 9 p.m. and 9:30 p.m. Why not 100%? Because when you're talking about probability coming through a drive-thru, can you really determine if it's going to be, between 9 and 9:30, I will 100% get a car through the drive-thru? No, we can't say that, because what if the roads are closed or there's flooding? You won't get a car that day, right? But you can say with 99% certainty between 9 and 9:30, we will get a car through that drive-thru. And I will show you how to do this with your calculator after we walk through this just with words. Alrighty, part C is graph f. So with your calculator, you're going to hit y equals. So hit y equals, top left, input the function into y1. So the function is 1 minus e to the power of negative 0.25x. Then you're going to hit the window button. Then for your x minimum, it's going to be 0 because time cannot be negative. Your x max is 30 because we do it to 30 because that is the maximum time after 9 p.m. that we calculated. Your y minimum is 0 because you cannot have negative percentage, and your y max is 1. We make 1 our max y because 1 equals 100%, and you cannot go above 100%. And that would be our graph. So what you would do is, I'll show you on a bigger screen, that's what our graph would look like, and you would just copy it. You see how there's no tick marks here? There's only the one tick mark. There's only that one tick mark. That's a big indicator, and there's 30 here. So part D, what does f approach as t increases without bound in the positive direction? So as time passes, the probability that a car will arrive increases, right? Because as time passes, it's like someone has to come, right? So the value of f approaches can be found by letting t go towards infinity. Now, what value is that? It's 1. Why do we say 1 is the value? Because you cannot go above 100%. So as t approaches infinite amount of time, it'll only approach 100% closer and closer and closer. So you'll go 0.99998. 0.999999998 and so on until you get to 0.99999 infinitely. All right, there's a part E that is not on here, but will be on your homework. So part E is asking when is y equal to 0.50? So wherever you are on your screen, on your calculator, press trace and then use the arrows to scroll around when y is 0.5. It occurs between 3-ish to 4-ish, so it's going to be 4 minutes. Now, what does this mean? So this means after 4 minutes, or 9:04 p.m., the probability of a car coming through the drive-thru is 50%. So just hang on, I'm going to switch screens and I'm going to show you how to do all of this example with our calculator. So still have your notes ready next to you, and then we're going to use our calculator. I'm going to walk you through this all with our calculator.
Alright, so with our calculator, we're going to hit y equals, top left corner, and then we're going to type in our function. So we have 1 minus e, so second divide, to the power of negative 0.25 xt theta n. It's just x, it all means the same thing. And then we hit window. So our window, remember we said it needed to be in between a few things, so the x minimum should be 0 because you cannot have negative time. X means time in this case. Your maximum is 30 because that's the biggest number we have. Your minimum is going to be 0 for y because you cannot have negative percent. And your maximum is just going to be 1 for your y max because 1 means 100% and you cannot go above 100%. From there you hit graph, top right, and there's our graph. Do you notice our tick mark for the y-axis only goes to 0, 1? See that little tick mark there? And then we have 30 tick marks on the bottom. So that's how we would graph it. Now if you want to go back home, hit second mode. Now we have to plug in our A and part B. So for A, we plugged in 5 because it was 5 minutes after 9 p.m. So we have 1 minus E, so second divide, to the power of negative 0.25 times 5. And we hit enter, and we get 71%. So 0.71, that's about 71%. Now we need to do the same thing for B, but this time with 30. So we have 1 minus E, so second to the divide, to the power of negative 0.25, parentheses 30. And we hit enter, and we get 0.999994, whatever. But it's 99%. Remember, it's never 100% because we can never go, you can't be 100% certain that a car is going to come through that drive-through.
Now we're going to show how to graph using my math lab. So we hit click to enlarge graph. We're going to hit exponential tool, and then we're going to hit 0, 1. So you see the top right in yellow where it says 0, 1, so we hit that point, and then our little box is going to come up. So make sure your base is the same, so it is. And then we have negative x. So negative x, if you think about symmetry, when you replace x with negative x, isn't that y-axis symmetry? So we reflect over the y-axis. And then for our negative 4, that's how much we're going to shift up and down. So we're going to go a vertical shift by 4 units. And then we hit save, and there's our graph. So the domain of every single exponential equation is negative infinity to positive infinity. Your range is always going to be your horizontal asymptote. So since this is a smiley face, or it's kind of a smiley face, you're going up. So if you're going up, you're positive infinity. So it's going to be negative 4 to positive infinity. Now, it's a parenthesis around negative 4 because we know it never actually crosses negative 4, it only ever approaches. So it's only going to be able to go to negative 3.99999 infinitely, but it will never ever cross negative 4. That's why it gets a parenthesis. And then our horizontal asymptote, it only ever has 1, and it's always going to be that number on the outside, so it's y equals negative 4. Our intercept, so our intercept is going to be where it crosses. So it crosses at negative 1, negative 2, at negative 3. So it just wants the number, so just negative 3. I'm going to go over another one with you guys. So we hit click to enlarge graph, and we hit exponential tool. The first point we plot is always 0, 1. So make sure your base is the same. So our base is 2. Okay, we're good there. So now we have x minus 3. So that's a horizontal shift because it's with the x. So x means shift left or shift right. So since it's minus 3, we're going to shift right 3 units. And then we have a 2 on the outside. So that means we have a vertical shift up 2. And there we go. So our domain, again, is always negative infinity to positive infinity. Why? Because it's an exponential function, and x could be anything. Our range is always going to be whatever that number on the outside is. So since we're going up, it's going to be parenthesis 2 to infinity. If you were going down, it would be negative infinity to 2. Our horizontal asymptote, there's only ever 1, and it's y equals 2, because it never crosses 2. For the y-intercept, use your calculator. So we have 2 plus 2 to the power of x minus 3, so 0 minus 3. And we get 2.125.